All right, so now we've got question 5. What's going on here? Okay, so we have question 5, and we have essentially two particles. Now, one of our particles, P, is telling us the position function from 0 to 8, and the other particle, Q, they're telling us our velocity. And they also tell us particle Q's particular position at a certain point. So I can go ahead and tell you that there is parts of this that is no longer applicable to the AP exam. And that is part, let's see here. I believe it's part D that's no longer applicable to the AP exam. Because they want us to essentially integrate velocity and go back to position. You technically don't do that on the AP exam this year. However, we'll still be practicing integration and plugging in, which is still on the AP exam, so we'll do it anyways. It's not too much of a leap based on what we've already studied. Okay, so for part A, one is particle P moving to the left. Okay, now it's going to be moving to the left when the velocity is negative, so we're going to find the position, or sorry, we're going to find the velocity function. So we're going to derive this, which is equal to the velocity of particle P. You might want to write that, which equals, well, let's derive this thing. We're deriving this ln structure, and this is, again, where we really get to drive home the point of what ln truly is. ln derived is the inside derived over the original inside. All right, so when we get to integrals with ln, that's something super important to remember, that really when you see a derivative over its original expression, if you can see that somehow, it might be scaled by some constant, but that's what ln really does when you derive it. You derive the inside and then you put it over what the inside used to be. All right, anyways, so now the question is, when is this particle moving to the left? So I'm going to make a sign chart here. I think I'll do it like this. Actually not. There's some place on the AP exam where they really go into detail about how to write sign charts. And I think I'll link to that later. Okay, so first things first, the important points here for the numerator is 1. So we definitely need to know what's going on at t equals 1, because that's what makes the numerator 0. In other words, it can change signs around there. Now this quadratic, so here t squared minus 2t plus 10, factors of 10 are, I don't think this factors. It doesn't. The question is it real or imaginary? I'm not sure. So I've got to actually do the quadratic formula, which is negative b plus or minus the square root of b squared minus 4 times a times c. Okay, I have my answer. This inside is going to be negative 36. It's going to involve I. So this is never going to change signs. In other words, our roots are imaginary, so we're either always sitting above or below the x-axis. And it looks like, I don't know, let's plug in 0. If we plug in 0, we get 10. So this is positive all the time. So this actually didn't need as much work as I thought. This is positive all the time. At 1, we have a different thing going on here. Make this look a little nicer. So the denominator is positive always. The numerator, if you plug in something less than 1 like 0, you'd get a negative. If you plug in something after 1, you'd get a positive. So here we have negative and positive. Okay, so when is the particle moving to the left? So P is moving left for this interval. From 0 to 1, it's moving to the left. Now, actually, I'm going to check myself right here because I used essentially what would be closed brackets. Because even though the velocity is 0, I kind of saw this on a previous AP exam question. I want to see what they end up saying. Yeah, see, well, now I'm just upset. So don't include the 1 because that is where it becomes 0. Interesting. I think they might have made a mistake somewhere on question number 3. If you remember, they had some weird stuff going on there. All right, anyways, back to it. So that's when it's moving to the left. Based on that sign chart, that's our argument. So up next, we've got, for time 0, 8, find when the two particles are traveling in the same direction. Okay, so we know that for part A. Let's find that for, or in other words, we know when particle P is moving left or right all the time. Now we need to know when particle Q is moving left or right all the time. And so particle Q, PQ of T, looks like it factors this time to T minus 3, T minus 5. And again, this is a quadratic, so let's see here. We're going to have VP of T that we're comparing, and we're going to also have VQ of T. This time, the things to care about on our sign chart are 1, 3, and 5. Okay, so for P, we know that it's negative when it's less than 1, and it's positive all the other times. And for particle Q, we have a sign chart here. Now left, again, this is a quadratic with roots 3 and 5. If you can picture that quadratic, it'd be something like that, which means it's going to be above, above, below, and then above. All right, so that means when are the particles moving the same direction? They are moving the same direction for, gosh, now I'm going to try to guess the sign chart even more correctly. 1 to 3, now I don't think we can really include 1 or 3 because one of them changes, you know, there's some change going on. So I think we have to only take the internal value there. So from 1 to 3 and from 5 to infinity. Or actually we should say 5 to 8 because they told us both of these only exist up until 8. And we should include 8 because that's just kind of the end, I think. Gosh, I hate these endpoints. Let's see here. So yeah, they're using a sign chart argument. And yeah, so 1 to 3 non-inclusive, 5 to 8 inclusive. Gosh, I'm finally getting the hang of it. Okay, part C. Now, honestly, if those brackets aren't totally correct, I'm not sure how much off that would be, but we could probably look through, you can look through some of the, what's it called? They have student responses on the page if you go to AP, and you can read through student responses and you can see what they might have done if some of those parentheses and brackets were off. But hopefully you're getting the hang of it just like me. I feel like I'm getting more confident in that. Okay, anyways, find the acceleration of particle Q at time 2. So whenever you do this, you don't just want to write a Q of T. You want to really show off that you know that that's by finding the derivative of velocity. So that usually will get you a point if you write that. Maybe it did this here. But when we derive that quadratic, right, again, it's just going to be 2t minus 8. And so the acceleration, I should put a Q there. The acceleration for particle Q at time 2 is -4. Okay, now they ask if the particle is speeding up, slowing down, or neither. So to do that, we need to say that VQ of 2, the velocity at 2, what is the velocity at 2? Well, I know it's positive, that's what I know, but I guess I could find it for real. That's 4, so it's 19, wait a minute. Oh, yeah. 19 minus 16, so we get 3. We have VQ of T is 3. We have AQ of 2 is -4. All right, so since V of Q and A of Q are different signs, positive and negative, at t equals 2, the particle q is slowing down. All right, so if both signs agree, the particle is speeding up. So that means if it's positive positive or positive negative, they will be speeding up. You'll either be moving faster downward or moving faster upward. But if they disagree, you are slowing down. Now, other things, obviously, if A of 2 was 0, then it would be neither. And likewise, if V of 2 was 0, even if acceleration was being applied, it would also be neither. So kind of tricky there, but you can review that concept back in, I think, applications of derivatives. They definitely go over that there. We had a few Khan Academies on that in the past. Okay, find the position of the particle the first time it changes direction. Now this is the part where we are definitely not doing this on the AP exam. So the first time particle Q changes direction, we did this, it's at 3. That's when it goes from moving to the right to moving to the left. All right, so we're looking for essentially, I'm gonna write it like this, the position of particle Q at 3. And the way you find the new position of a function is you take where you last knew you were, and they told us that we were at 5 last time we knew, and that happened at time 0, but we want to go to time 3, and the way you find position is you integrate velocity. So this is how you would find the new position. Now again, this is out of the AP exam, but it's still a good kind of general concept to know, especially if you plan on taking Cal 2 or maybe Calc BC in the future. So we have 5 plus the integral of 0 to 3 of this quadratic structure. All right, and this is going to be 5 plus, we'll get t cubed over 3 minus 4t squared plus 15t. Luckily, we're evaluating this at 0 to 3. Because when we evaluate this at 0, thankfully all that goes away, so it's really just 5 plus, let's see here, that's 9 because it's 27 over 3. That's negative 36, and that's 45. Right? So we've essentially got 50 minus 27, which would be 23. So that is the position of Q at 3. So maybe I'll just write that, since I didn't technically define it as, well, I guess I did, but and there we go. Did I get it right? Yes, I did. Okay. And that's it. Yay, we did it.